Good morning, you 11s. We're back. We're back. Oh, guys. Oh, you 11, how you been getting on? I know I've just started it. I kind of hope that you guys would be kind of sitting there kind of going, he's gonna do it any second. We will see how long it takes for you guys to log in and recognize that I've gone live on our lesson. Hey, look at that. Ashy Potato. MJ's in the house. Elijah's in the house. Morella's in the house. Wait, look at this. Everyone's like, boom, boom, boom. Who's Didney? I don't know who Didney is. I've got Catherine, got Tom, got Harry. Woo! Smashing this. Right, I'm just turning off my other computer. So that way, there we go. We're back. Russell's Didney, of course. Thanks. Hey, Meryl. It's nice to see you. And I've suddenly realized I'm meant to be doing a register. Oh, no. Let's see if we can get this all up and running. So how is everybody doing? Is everyone feeling a bit like me? Like, I'm kind of glad to be going back like to this. But on the other hand, I really didn't like waking up so early in the morning. Right. Who do we have? I don't know which laptop I should be doing this on. I'm like, right. Who do we have? We've got MJ. There's MJ. Have we got Audrey? I've seen Elijah. Seen Tom. We've got Ansh. Who's in here? Have I got Ansh? Haven't got Ansh yet. Got Meryl. Whoop, whoop. Got Harry. Got Aisha. Anyone seen Aisha? No? Haven't got Hibby yet. Got Marella. Who else have I got? I've got Marcellus. Brain mushy. I totally know the feeling. Have I got Isha? Yes. Yo, Isha. Hey, Emmeline. Oh, do you know what? I miss you guys so much. Oh, I want to go back to school and set fire to kids. No. Oh, I'm live on YouTube. I don't really set fire to kids, figuratively speaking. Yes. I just want to set fire to stuff. This is really tricky. Meryl, don't give me a sad face. You missed the fire too. Michael's in the house. Hibber's in the house. Got Hibber, got Emmeline, got Russell. Have we got Russell? Has anyone seen Russell? Did I see Julian? Is Julian here? I saw Julian. Yes, Julian's here. Hibber? Anyone seen Hibber? That's not much better. Oh, funny. Has anyone seen Minwee? There's Hibber. Whoop, whoop. Or Audrey. I know that there were a couple of people who've always had trouble. With internet and whatnot, and you guys are always really good at being able to fill me in with the gaps. So I'm missing Sian, which I didn't expect. Oh, I've got a Liz. Oh yeah, I've already marked her in. Got it. I'm missing Sian. I am missing Aisha, Ansh, Minwee, and Audrey. Oh, there's Aisha. There she is. Whoop, 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 whoop. Yeah, we're getting there. Come on, guys. Oh. I didn't dab. I am suddenly remembering that there are other people now watching these videos. Oh, no. Minwee is here. Yay. Good to see you, Minwee. So, year 11, is everyone okay having spent 2 weeks on lockdown? We're back to full school again. I just want to check that nobody's like bought themselves a melon, painted a face on it, and have started calling it Wilson. No one started doing that, right? Because if you have, that's a worry. Yeah, just Hoping that everyone is all okay. I'm still missing Audrey. Has anyone seen Haven't You? Beryl! Don't say that. I could sleep more. That's all you've got for me, MJ. That's it. Same. You'd be the first person I'd expect to. Oh, I never do that. Ah, I am totally sane. Completely sane. Right, so I am now missing 2 people. Did someone say that Audrey's here? Has anyone seen Audrey? No? Or Ange? Can somebody message Ange, please, and tell him to get out of bed? Sheesh. Blimey. Right. Okay, folks. So we can crack on today now. Right. So I'm going to share my screen. And today, you guys all know what I'm doing. So I'm going to share screen. Go, go, go. That one. Hide. Onto here. Did I just see somebody else has messaged in? Ange is in the house. A little bit late there, Ange. Yeah, a little bit late. Right. Okay, folks. We are starting on with paper 2. And it's a 1-hour paper. We know that the paper 2s are always a little bit shorter, which is really nice. So we can kind of move straight on with this. Could someone just give me a heads up on whether or not Audrey is able to attend? Right. Mr. Duncan looks so offended. She's trying to get online. Okay, no problem. Thanks for letting me know. Sorry, I just woke up. Nice one, Ange. Right, guys. So today we're doing June 2016 paper 2. You'll notice that I have gone on to, just to quickly show you guys, I have gone on to, no, don't that one, don't that one, don't that one, don't that one, don't any of these. Hang on. I need to go back to all these. Right. Oh, yeah, that'll actually do. Paper scores. Guys, I realize, having had those conversations with you, that lots of people have been doing other papers, and I've just started. Yes! Whoever added in January 2018 and paper 2 January 2018, thank you so much. That is exactly what I wanted. I was hoping that you guys would just start adding in your papers as necessary and then inputting your data. Guys, I do want you to continue to add on this data. Yeah, please, please keep doing it. That is great. I'm really, really pleased to see that you've been doing it. Thank you. That's fab. I'll change that to spec paper just to make it fit better. That was me. Thank you, Harry. Really appreciate it. That's awesome. Year 11s. There are only a handful of you guys who are inputting your data. I want everybody's data, please. Yeah, please, 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 please. Please, please input your data. Okay? Oh, no, gone Yorkshire. So, going to start with paper today. So, I've got paper 2. I'm going to do as many of these. You guys know I've got 3 weeks where I'm going to be doing a paper a day, basically. Paper a week. Trying to get through as many of these as I can, because I'm going to be starting to teach you guys A-level in 3 weeks' time, which is well exciting. I am super duper excited to be starting A-level with you guys, which is going to be amazing. Surname, Duncan. Yeah, first name's Awesome. I should change my name to Awesome. That'd be amazing. Or maybe even like, I don't know, Danger. I think Danger Duncan. That'd be pretty good. Shout out to Miss Burton Morgan. She used to call me that. There you go. Right. Okay, folks. So question number 1. Hydrated copper sulfate is a soluble blue solid. By the way, it's really nice for me to do all the usual extension bits. Hydrated copper sulfate. I shouldn't be circling it, of course. I should be circling it in dark. It's a very blue. It's very blue. Yeah. Hydrated copper sulfate. There we go. You guys need to know this guy. And it is important just for me to remind you, Cu copper sulfate dot 5 H2Os. EdXL, could you resend the link to that, sir? Yes, of course I can. Absolutely, Michael. Share. Michael. Let's go for that. Michael. Should come up pretty easy. Or not, as the case may be. Michael Z, there you are. Send. Anyone else need it? Fab. Right, let's go back to the lesson. Yeah, that Edexcel, love the fact that you've got to know that. Yeah, so just bear that in mind. After 2 days, so this is a diffusion practical in paper 2. I like it. I'm actually going to leave those. I'm going to put those back, although I don't want that one, just want that one. Okay, after 2 days, the crystals become smaller and the liquid near the bottom of the beaker becomes blue. Which statement explains these observations? Right, so the crystal is dissolving. The crystal dissolves. Definitely, I'm going to change that to, I'm going to go for black. There we go. Oh, okay. So the crystal dissolves, number 1. And then after 2 weeks, the crystal has disappeared. So that explains the first one. Now, lots of people are going to be looking for diffusion. Yeah, because we realize that it is diffusing. It's diffusing outwards like this. Yeah, but the process originally, from the beginning, because there's no diffusion in this selection, it's the dissolving process they're wanting here. Yeah, and then they're going to say, after 2 weeks, the crystal has disappeared. Which statement best describes the appearance of the liquid in the beaker after 2 weeks? It will all be blue. Yeah, it is all blue. There we go. So this is after 2 weeks, guys. And after 2 weeks, diffusion would have finished. Yeah, definitely. So the entire beaker will have gone, will this blue, yeah, the blue would be evenly distributed. Yeah, we remember that whole description of diffusion. The description of diffusion being this idea that particles move. Yeah, if I just do a little quick note on diffusion, because it's so common. Yeah, diffusion. Particles, bullet point number 1, particles move from area of high concentration to low concentration. Particles move from area of high conc to low conc, and then it will continue doing this, yeah, until distributed evenly. Yay. So until distributed. So that's just me just reminding you of diffusion. Next, the formula of the compound in the crystal is .5. How many different elements are in this formula? So I have got copper. Let's highlight them. Copper, sulfur, oxygen, hydrogen. The answer is 4 different elements. Yeah, 4. How many atoms are shown in the formula in total? So, okay, we've now got 1 copper, 1 sulfur, 4 oxygens. Here's the trap. 10 hydrogens and 5 oxygens. Add those all together and I will get 21. So 21 atoms shown in the formula in total. Seem reasonable? 4 elements, copper, sulfur, oxygen, and hydrogen, 21 atoms in total. 1 copper, 1 sulfur, 4 oxygens in the sulfate, and then 10 hydrogens and 5. And I've just added those all together to give me 21. Okay, I like it. Iron is a metal with many uses. One problem with using iron is that it rusts. Name 2 substances needed for rusting. Oxygen and water. We know this. We love rusting. Next, state the name of the main compound present in rust. Right, guys? So this one, low level. Yeah, this is like a love 4. Love 4, 5. Love 4, really. And then this one's a bit trickier. This one jumps. This is a love 7. And it's purely because most students, the most common error is students will write down iron oxide and you will lose it. Yeah. What do you need to make sure you have, folks, to get that mark? What do you need to get it? Let's see how long it takes someone to give me an answer. Come on, come on, come on, you livin'. It's the U11 song. Sorry. I'll stop. Come on, come on. Give the charge. Yes, Harry. There we go. Love it. Iron 3. No, it's not oxide. It is oxide. It just needs its Roman numeral, Ira. Yeah. It says except iron oxide. Yeah, Anch, they usually don't. Please, please, please don't. Yeah, if you put iron oxide, lose it and put the 3 in. That is very common. Yeah, and I do want you to be using it. Edexcel have done both tricks, and that's actually very unusual for them to say except iron oxide. You should be iron 3 because you can't get iron 2 oxide as rust. It doesn't happen. Next, protecting against rusting. We've talked about this. We did this in year 10, of course. We talked about how there are loads of different methods of protecting against rusting, but excuse me, each method has certain pros and cons. Yeah. So galvanizing is covering it in zinc, and you wouldn't do it for a bicycle chain because it's going to move and scratch off the metal. You would use it for a bucket, absolutely. So a bucket, we would definitely galvanize. Yeah. Car body, no, that would be a very expensive process. We'd paint that. A car engine, not really. Although potentially parts of a car engine would be. A food can, yeah, probably. No, you can't. Zinc's too reactive. Yeah, wouldn't do that. Railway bridge, no. Too expensive. Okay, so oiling. It's going to be a bicycle chain and a cut. Do you have to put, choose 3 of the objects to put in the table. Bicycle chain, definitely oil. And also car engine, if you like. Let's get rid of those. Painting, car body. Yeah. The reason, that's a really interesting question, actually. It's really interesting because they've given you these 6. Yeah, so a bridge, you would paint. Yeah, car body, you paint. Bucket, you galvanize. People often ask why, because buckets are usually left outside in the rain, and they often get bashed and dented. Yeah, now some people would argue that about the food can. They'd be like, well, hang on a minute, food cans get bashed and dented, yes, but you can't use zinc on a can because on the inside the zinc will react with the food. It's a relative, I mean, even though it's relatively unreactive and you paint it, but the food's acidic, you see. Foods are slightly acidic. So we actually coat them in aluminium, is what they're doing. Car engines are too complicated. Car engines have a mixture of everything. Some of the pipes will be covered in chrome rather than zinc. You wouldn't want to use zinc because the engine's going to get hot and it'll then cause the zinc to oxidize and turn into zinc oxide. That wouldn't be a good choice. But lots of oil, chrome. Bicycle chains, of course, are always oiled. Yeah. But anyway, really interesting question, though. Next, an iron object is coated with zinc to protect it from rusting. This protection continues even if the zinc coating becomes scratched. Explain how the zinc coating protects from rusting. Right, this is called sacrificial metal. Sacrificial metal. And what happens is if you have a surface of an object, and that surface is made of iron metal, yeah? That surface is made of iron. What you do is you then, of course, cover it in zinc metal, and that zinc acts as a protective layer. Now, the thing is that people then go, oh, but what happens if it gets scratched? It's going to then, that's what happens usually with paint. You scratch paint and it will start to rust immediately around that scratch, but it doesn't happen. It doesn't happen when you galvanize. I'm going to zoom in on this. Now, the reason being is because it acts in this very unusual, what's called sacrificial metal. Because what now happens is the oxygen will be able to get into the crack. Yeah. And so we would have the iron would react with the oxygen and the water, and it would turn into iron 3 oxide. Balance the equation. 2 to give me 6 to give me 4. Yeah, but here's the cool bit. The zinc immediately reacts with the iron 3 oxide because it's more reactive than iron. So you then get zinc oxide, which is just ZnO and Fe, and then you can balance it as such. Gonna need 3 zincs for the oxygens. Gonna need that one, and then we're gonna need 2 ions. So it actually converts it back. So you would say, how would it prevent it from coating? So you could say zinc metal. The sacrificial metal, by the way, is probably going to be a mark somewhere. I'm going to want to mark this straight away, by the way, because rusting's a rather odd one. Zinc metal is more reactive than iron. So will reduce any iron oxide. You could also talk about this in terms of electrons rather than oxygen. So we'll reduce iron oxide, iron 3 oxide when formed. Want to mark that now? That's a very good question. Really like that question. Let's actually go and mark that straight away. So now you realize, even, I mean, guys, I'm always brutally honest with you guys. Yeah, I always want you guys to realize, oh, they're not on this exam. Hang on a sec. They're on my other laptop, but I can get those. Let's have a quick look. Yeah, I'm nothing but honest with you guys. Even I'm like, that's a tough question. It's very wordy. Definitely want to see what that actually looks like. 2016. This is the 16, isn't it? We'll know immediately from question number 1 anyway. There you go. So A and A, it's all blue. So I think we got the first 2 correct, didn't we? Yep. Tick and tick. It's always good. 4 and 21. I like it. Next one, oxygen, water, and iron 3 oxide. And somebody said it accepts. There you go. Except iron oxide. I don't like it. There's the correct answer. Oh, hydrated. Oh, that's interesting. Except .xH2O. Isn't that cool? I like that. That's actually very true, by the way. Galvanizing oil paint. Cool. Zinc oxidizes react in preference to iron. Interesting. Ignore reference to sacrificial metal. Oh, okay. Except zinc atoms react with iron 2 ions. Ooh. Zinc is more reactive than iron. Zinc loses electrons more readily than iron atoms do. Oh, okay. Zinc reacts in preference to iron. Zinc is more reactive. Okay, so we get that second mark. We definitely get the zinc is more reactive than iron. We get that mark. But I definitely wouldn't say I would have got the first one. Yeah? So we can say, I don't really like it, to be fair. Zinc atoms react with iron 2 ions. That's interesting that they don't allow, they should. By the way, I would argue it. Yeah, zinc oxidizes, reacts in preference to iron. I'd probably say I've seen so many different varieties of that, and you had to give half equations and everything, which was really, really hard. You guys remember that, don't you? The really hard version of this question, because what is actually happening is the zinc atoms are reacting with the iron, and interesting that it says iron 2 ions instead of iron 3. It's very interesting. Iron 2 plus to form zinc 2 plus, and iron metal turns it back into iron. Yeah, and the 2 half equations are zinc is losing electrons. Yeah, it's losing 2 electrons, and iron 2 plus is gaining 2 electrons. See, Edexcel have got these really bizarre idiosyncrasies. They should be accepting iron 2 or iron 3 ions. I don't feel like there's enough there. Anyway, I'd definitely say that there's room for me to improve on that question. I'll work on that. Next question. Going to get rid of my mark scheme, go back to my chat in case you guys are saying anything. Nope, no comments yet. Still got 20 people watching, which is great. Okay, this question is about gases present in the air. Which is the most common gas in dry air? How bizarre. Nitrogen. Weird. Which gas makes up 1% of dry air? 1% argon. That's really interesting. I've never seen them do that, folks. Never seen them ask about argon. Nitrogen we know is 78. Oxygen is 21. That leaves us with 1%. Yeah, and remember that carbon dioxide is 0.04. Like, it's tiny. Yeah, so argon is the only one left there. Argon, the stranger. Yeah, that's what the argon comes from, Greek or Latin for stranger. It was discovered by Ramsay. First noble gas to be discovered. A piece of copper is heated in air. State the formula and color of the compound. Oh, cool. So copper oxide. And by the way, note formula. If you write name, you lose it. My Wi-Fi died. Sorry, Mr. Duncan. Oh, Sian. Hello. Did I do the register with you on it, Sian? Nope, there you go. You're in, Sian. You're in. I have updated the register. It's good to see you. Color, black. Black! It's a black compound. You've got to know that one. So copper starts off as pink. just nice to show you this. Yeah, copper starts off as a pink metal. So copper metal, there we go, images. Starts off pink, look at that, isn't that pretty? Yeah, that's copper, that. So copper, pink, but if you heat it, turns black. Copper, heat, copper metal, heat. Oh, first, I love that. Love to see the change in the color there, the oxidation process. That's really cool. Tempered colors. Wow, neat. But if you heat it, of course, in reality, eventually it just turns black. Let's do copper oxide. Copper oxide. Sorry, that's the copper oxide song. There we go. Now, that's cool. Look at that one there, folks. That's gone green. So copper tends to turn black and then turn green. Would anyone like to offer me who's the green color? So copper, I need pink. Hello, pink. So it starts off pink. Hello, there's copper metal. Starts off pink. Heat it in oxygen. So do plus O2, and I get black. Black copper oxide turns black into CuO, and then it turns green over time. Would anybody like to tell me what I have become? It's actually not green. It's actually not green. It's actually turquoise. Well, if we're gonna do it, let's get it right. Yeah, it's like it's a turquoisey color. It's actually said to be blue-green. At Excel. Malachite. Oh, well done, Harry, for remembering its common name. Hibber, great job. Copper carbonate. Oh, guys, well done. Super proud of you. Yeah, we end up with copper carbonate, which is turquoise. And by the way, copper carbonate as an ore, it's rock. Yeah, the rock. The rock is called malachite. That's the common name for the ore, malachite. There we go, and that's the ore of it. I don't think that's how you spell ore. No, it is something like that. Anyway, next question. What is it reacting with? Go on, folks. You guys are doing great. What's it reacting with to turn into copper carbonate? I'll show you some famous copper carbonates. Who's going to get it? Well done, Hibbo. Good job. People often ask why the Statue of Liberty is green. It's because it's covered in copper carbonate. Well done, Michael. CO2. Spot on, dude. Tom, well done. Great job. It's reacting with carbon dioxide. Yeah, that's what it's just reacting with CO2 in the atmosphere and turning into copper carbonate. And this is why the Statue of Liberty... So guess what the color of the Statue of Liberty was before it turned green? It was pink. Can you believe that? The Statue of Liberty was originally pink, then will have turned brown because it'll have picked up a small amount of the way that coins do. Then it will have turned black, and then it will have turned green. Isn't that cool? Statue of Liberty original. There we go. Look at that. It used to be pink. It used to be, it's solid. Isn't that amazing? It's made out of solid copper. Amazing that. Made in France, given to the United States as a gift. Amazing. Anyway, back to it. Sorry, I'm getting distracted by cool chemistry. Right. Okay. Tap funnel. Oh, I'd excel on the tap funnels. The diagram shows apparatus used to prepare carbon dioxide in a lab. The liquid in the tap funnel is, well, that's interesting. Let's give you no, fascinating. So the liquid's going to be any acid, except you wouldn't want to use concentrated sulfuric. That would be terrifying. No. Dilute hydrochloric. And then the solid in the conical flask is calcium carbonate. Calcium carbonate! If you're wondering why you wouldn't want to use conc sulfuric, the reaction would be excessively violent, and it would create the gas so readily it would probably foam up. Conc sulfuric acid. Hang on a sec. No. Oh, guys. right? Just to explain why. Calcium carbonate reacts with hydrochloric acid to form calcium chloride, CO2, and water. Yeah? But, great chemistry. Guys, that reaction there with sulfuric acid stops almost instantly. The acid would go in and then there would be no reaction. There would, but it would stop pretty much instantaneously. The reason why is you're going to make calcium sulfate, which is insoluble. You'll get 2 bubbles and it'll stop. That's it. The reason why is, imagine this is the calcium carbonate rock. Well, when the hydrochloric acid reacts with it, you see the reactions at the surface, the CO2 bubbles away, as a gas, that leaves as bubbles, but then the calcium chloride, which is formed, dissolves into the water, yes? But if you do the same thing with sulfuric acid, what happens is you form a layer of calcium sulfate over the surface, which seals it. That's calcium sulfate solid, which is not soluble and therefore stops the reaction. So actually a much better reason other than being too violent, it's actually not going to be violent at all. Lime water can be used to test for carbon dioxide, include state symbols. Well, you know that carbon dioxide is gas. There's lime water, folks, commonly known as chemical name, calcium hydroxide, common name, slaked lime, and when in water, aqueous lime water. Then you form limestone, which is a solid, and liquid water. So there's your precipitate, folks. That's why it turns cloudy. Yeah? Cloudy. Yeah. Cloudy. I don't like cloudy. White precipitate. State the observation made in the test. White precipitate. Precipitate. There we go. Better to use white precipitate. It's better, more A-level than GCSE. You're allowed to say it turns cloudy, but I don't like it. I prefer white precipitate. It's much more higher level. Next. Piece together electrolysis. Okay. Fine. Right. Okay. So these are going to go down here. Going to put the little corks with the electrodes. That was terrible. Cork with the electrodes on. There. There we go. And then we're going to have test tubes over the top of them to collect the gas. Yeah, and then a battery, and then solution. Yeah, and then over to the battery. I don't like that. I don't like it. I prefer doing so the wires aren't touching like that. Love to see the mark scheme on that. Next, half equations. Okay, show the half equation for the reaction at one electrode. Right, ooh, what's the polarity? Oh, that's just mean, isn't it? Wow, don't like that. That's a really clever trap, isn't it? Right, so they've got KCl in the solution. Right, you're making hydrogen gas. The other one, you're going to make the chloride ion. 2 of them are going to form chlorine and lose 2 electrons. Notice the electrons are on opposite sides. Year 11, I am going to be teaching you guys A-level redox next. Maybe not next lesson, depending if I finish the paper. As soon as this paper's finished, I'm going to do redox and I'm going to teach you it at A-level standard. Because it's easier for me to do that because it means that I've discovered that EdXL, the questions at GCSE just really don't follow the specification. They're so far beyond GCSE spec that I may as well just teach you it at A-level, and that way you can do the GCSE questions more easily. It's just better for me to do that. So now that's going to be occurring at the positive electrode, and that's going to be occurring at the negative electrode. I'm just wondering whether or not they want me to write the words or just the symbols. Yeah, I'm going to put, that one's at the positive, and this is at the negative. Now, can I just point out that everyone in this room should be saying that equation's incorrect, because it is. Yeah, but they've done it deliberately to confuse everybody. Yes? What should have been happening there is that the H plus ions were reacting and gaining 2 electrons to forming hydrogen gas. Yeah, that's what it should have been. But Edexcel are being sneaky. So just being aware of that. They're trying to trip you up. Next, describe a test to show that the gas collected is hydrogen. Light the gas, collect gas using lit splint, light gas, squeaky pop sound. And then you have all of the alphabet, squeaky pop sound. We're done. Just to show you what the equation is, the hydrogen is reacting, is combusting with oxygen to form water. That's French for water, if you didn't realize. And so that's the actual reaction taking place. It's just a combustion. And it whistles because the tube is acting as a whistle. Sir, you lose marks on the diagram because you did not label the solution. Thanks, Anch. Fanch. KCL. Fine. All right. I'll lose 1. All right. You happy? Fine. They did 2. Do I need to label the wires? They're labeled in the picture. My name's Anch and I know everything. I'm a good chemist now. And that's actually true. You're actually becoming a very good chemist. I'm very proud. Very proud. Right, next. I'm very aware of the time. This lesson finishes at, I can't remember. Is it 25 normally? Nah, you're good. Thanks, Ant. You're a star. Thanks for letting me know. I'm trying to find my timetable. Where's my timetable? Oh, no. Don't know. It's gone. Timetable's gone. Hang on. I don't know. I give up. Give up. Anyway, keep going. Atomic number of protons is 19. Atomic number is number of protons. Mass number is P's and N's. So now it's asking for number of neutrons. 39 minus 19 gives me 20. Winner. There we go. Next, I've got the atomic number of 19. That means I've got 19 protons. But this time I've got 22 neutrons. So I'm going to add 22. I'm going to add 22 to 19, and I'm going to get 41. And I kid you not, I'm doing that on a calculator because I don't trust myself at all. Winner! Thanks very much. Thank you. There we go. Next, right, work out the relative atomic mass using the relative ratios of the isotopes. So we've got 6 multiplied by 7.4 plus 7 multiplied by 92 points. I keep switching into Yorkshire. I don't know why. I'm so sorry, folks. I'll stop that now. I'll stop it. All over on. I can't die. I'm good. Okay. Okay. So it's going to be really close to 7, innit? We know that. It's going to be like 6.99 or something stupid. 6.6 times 7.4 equals. Oh no, I've typed it in wrong. 6 times 7.4. So easily done. Plus brackets 7 times 92.6 all over 100, and I get an answer of 6.926. So the relative atomic is 6.9, and I'm done. 1 decimal place. Yeah, it says that in the question, by the way, if anybody missed it. Easily done that. I've written down the real answer and then written down the answer they want there. That's always a better thing to do. Next, a reaction. Just to mention other versions of this question, guys, just to mention it. Yeah, other versions is they don't have to give you a percentage. They could just give you a ratio. They could have given you lithium 6 being in a 3 and lithium 7 being in 10. And that they'd say that this is the ratio is in a 3 to 10. Yeah. And then you just run the same process, 6 times 3 plus 7 times 10. But now you divide it all by 13, the total of the ratios. Just thought I'd let you know. Just thought I'd run that. A reaction occurs when a small piece of potassium is added to water. State 2 observations that could be made during the reaction. Okay. So with potassium, it's going to float. Yeah, we're going to float. It's going to fizz. Now, can I just point out, this is tricky, because we realize that we've got, this is lithium versus sodium versus potassium. Now, it's really interesting that because these two here apply to all of them. But there are some that are specifically for potassium, like it will catch fire with a lilac flame. Yeah, none of the others do that. But it'd be interesting to mark that. I kind of want to. Eek. Let's have a quick look. At that point, nitrogen, yep. Argon, yep. Black. Hydrochloric acid. Oh, I missed a question. Ah! Did I miss a question? Did I miss one? I missed a question? Oh. That's weird. Hang on, I've missed a question. Nobody pointed it out. It's so easily done when they're at the end of the paper like that. A diagram shows gas being collected over water. Suggests another way to collect the gas. Gas syringe. Yeah. I missed a question. So easily done. Can I just say, folks, that is normal. As I said, I like the transparency that I have whenever I'm teaching you guys. I like that transparency. Me saying, you know, everything that I do is what I would as if I was in an exam. And one of the things I always try to get you guys to realize is mistakes happen. I would have caught that one at the end of the exam because I would have gone through the exam paper. I would have literally gone through page by page going, right, okay, I'm with that, yeah, and then gone, oh, hang on a sec, I've missed one. I know at the end of the exam, everyone's always tired and you just kind of flick. I know that you might not even have exams, but, you know, it's something to be aware of. Just for future. You guys kind of missed that now. Oh, wow. Does it need to be uneven? Mark M3, solution placed in the vault labeled as potassium. Ignore all 3 levels of liquid. Yeah, damn right. There we go. Except I hate that, despise that. Despise the fact that they put negative minus electrons, hate it. Effervescence, fizzing, moves around, forms a, where's floats? Forms a ball, becomes smaller. Oh, floats, number 2. Okay, yeah, winner. Winner, chicken dinner. Did I just say chicken dinner? I didn't say chicken dinner. A few drops of phenolphthalein are added to the trough. A reaction occurs, state the final color. It turns pink. Yeah, phenolphthalein, P-H-T-H-A-L-E-I-N. Phenolphthalein is an indicator that reacts with alkalis. Yeah, in acid, it's colorless. Yeah, it's colorless in acid. However, in alkali, which is why they're called the alkali metals, it's pink. Yeah, so we know that we're forming, the potassium is reacting with water to form potassium hydroxide, which is why they're called alkali metals. 2, 2, and 2, I believe. I think that adds up now. Right, the electronic configuration of lithium and potassium are. Explain why potassium is more reactive than lithium. Right, so we're going to say the outermost electron in potassium is in energy level 4. Just to show you that, the outermost electron is in the 4th energy level, whereas lithium's is in the 2nd energy level. Outermost electron in potassium is in energy level 4. Lithium's is in energy level, I could just put level at that point, energy level 2. Outermost electron in, I wouldn't do that in an exam. I wouldn't do it, Tom. Missed another question. Damn it! Give the formula of an ion formed during this causes the color change. Thank you! That's so irritating. So frustrating. Thanks, Ange, for letting me know. Only one paying attention. Thank you. The ion form that causes the color change is OH minus. Yeah. Just to mention, by the way, they do need to be capital letters. There you go, Ange. There's my feedback to you. Got to make sure that you do capital letters on the O and the H. Outermost electron further from the nucleus. Outermost electron further from nucleus. Therefore more easily lost. Therefore potassium's electron is more easily lost. There we go. Right, guys, I'm very aware that we're nearing the end of the lesson and we've still got quite a few questions left to do. So what I'm going to do is I'm going to end part 1 here and I will finish this off next lesson, which I think is tomorrow maybe. So I'll draw the line. Gives you guys a bit of time to get to your next lesson. I don't want to kind of overrun. Let's do end of part 1. End of part 1. Do you know what? I'm suddenly realizing, of course, I need your help. Emmeline, you were so wonderful. I'm just going to bring myself back, guys, to the classroom. Sorry, hang on a sec. StreamYard, back to stop screen share. Ooh, we're back. Way. Right, guys. So, Emmeline, could you do me a massive favor? I'm not going to ask you to do it for this one because you'd have to go back through it. Although it would be really, really nice of you to be able to go through and time tag everything. If you get time, if you can't, don't worry about it. But from now on, if you could just keep track of when I do the questions, and that way I can then add on that timestamp, that'd be fab. Year 11, it's so good to see you all. I hope you guys all have a great first day back at school for term 3. Take care and be safe and keep working hard. Fill in the data on my sheet, please. That'd be amazing. Thanks, guys. I'll leave you be. I can do it in a bit. Thank you so much, Emmeline. Thank you. You're a star. Thank you. Thanks, Ange. Thanks, Ira. Thanks, Harry. You're more than welcome, guys. Have a great rest of your day. It's awesome to see you. See you later.